Alright, good afternoon everyone. We're going to go ahead and get into the second part of our video, which is going to deal with the equilibrium constant, or as we saw it in the previous unit, that KEQ thing that I kept pulling in as we were talking about kinetics. Now, you want to go ahead and take a moment to rate yourself and see where you are in terms of what you actually know already about the equilibrium constant. Some of you spoke to one person who said they had been watching videos on Khan Academy or other resources. That's perfectly fine. Utilize the tools that will be necessary for you to be successful on this exam. Now, our goal overall at the end of this video is that you will be able to explain the basics of the equilibrium constant and be able to use it to determine the shift in equilibrium for a particular reaction. Now, let's go ahead and jump in. Now, in order to understand what's going on with the equilibrium constant, we're going to bring in this term called the law of mass action, which basically states that a certain ratio of reactant and product activities reaches a constant value when the reaction is at equilibrium. In other words, when we look at our products and our reactants overall, there's going to be a certain value that's represented, or that can be representative of that point when the reaction hits equilibrium. This ratio is what we're going to call K, or the equilibrium constant. Now, this is how we're going to represent it. If you're given the following generic equation, J, which is J, K, L, and M, which are going to represent our coefficients for the balanced equation. We have A plus B yields C plus D. And we see that this reaction is at equilibrium. We can actually set up our Kc, or Keq, both are used interchangeably, to determine this ratio, where it's going to be our products, as we have here. See, our products are on top, over our reactants. Now, notice that here we're using the square brackets again because it's dealing with concentration, and Kc is just letting you know that you're dealing with the concentration version. There's another one that we're going to deal with very shortly, which is Kp, which is going to be about pressure. Now, the numerical value of Kc at a given temperature can be calculated if the equilibrium concentrations of a reaction are given. It's going to be expressed without units, so you don't have to worry about, like we did with the lowercase k for the reaction, the rate constant. This one is going to have no units involved. And if we have a pure liquid or a pure solid, it's going to be thought of as one. So we won't even include it in the equilibrium expression if it's a pure solid or a pure liquid. This is again why those states, those little states that we usually put on the side, are important, because this actually simplifies a lot of your work if you start to see these things show up in your equation. So when we're dealing with a balanced equation, let's go ahead and we'll walk through this one a little bit. Now, if we have an equation and we're going to adjust the equation, so we're multiplying it by a factor of n. The equilibrium for the new reaction, is going to be the original expression that we had raised to the power of n. So if I'm going to adjust this reaction that we have here, again going back to that Barnhaber process, N2 plus 3H2 yields 2NH3, and we want to multiply this by a factor of n. So we have n plus 3n, 3 times n, and 2 times n. When we adjust our equilibrium constant, you notice that that n now makes it into our equilibrium constant as part of our exponent. So it'd be the same as just multiplying it, and now we're raising those values totally to the power of n overall. We don't run into this often, but it's good to have it up there and be able to understand what's happening if you do have to make these adjustments. Now, if the overall expression is expressed as the sum of two or more steps, then Kc or Kp for the overall reaction is the product of the constants for the individual reactions. This is called multiple equilibrium. So if I have a mechanism given to me with 3 different equilibrium constants, when I multiply each of those constants together, it'll give me the overall equilibrium constant for the larger reaction, the overall balanced equation. Okay? Now, K always has the same value at a given temperature, regardless of the amounts of reactants or products present initially. So the only thing that's going to change this is if I adjust that temperature. Okay. Now, for a reaction at a given temperature, there are many equilibrium positions, but only one value of K. So I can find what we're going to talk about is Q, that quotient, reaction quotient. I can find that information at many different points along the equilibrium, but again, all it's going to tell me is which way the reaction is moving, whether it's proceeding forward or backward. But there's only one K value overall at that temperature. Now, K or Kc or Keq involves concentrations. Kp is going to be where we deal with pressures. We want to look at an example here of the same reaction, but now we're doing it in terms of pressure. Now, the way that you'll know that you're dealing with pressure is the values that they give you will be in atmospheres or torr or millimeters mercury, or last but not least, kilopascals, kPa. Now, if you see any of these values, usually we're going to want to transfer them back into atmospheres, and I'll talk to you on how to do that. But if all of them are given to you in this way, we're just going to plug them in the exact same way as we did before with our equilibrium constant. But now we just input the actual pressures. So looking at the example, equilibrium pressures at a certain temperature for the pressures of ammonia, 2.9 times 10 to the negative 2 atmospheres. You see the other values for nitrogen as well as hydrogen. And we're just going to go ahead and plug those values in. Once we plug those in, we get the actual final value, which is given to you here at the bottom of the screen. Just a matter of solving, okay? Not a lot of this stuff goes back to heavy math, but you will have to do a couple of things that you remember from algebra coming up a little bit later. Now, if I need to convert between the two, or I need to understand the relationship between my Kc and my Kp, it's going to be equal to, Kp is equal to the equilibrium constant times the gas constant, universal gas constant, which is given to you here on the bottom of the screen, that's R, times the temperature in Kelvin. Now, all of that, the universal gas constant times the temperature, is going to be raised to the power of delta n, or the sum of the coefficients, or the differences, sorry, between the coefficients for the reactants and products. This is going to be our way that we can go between the two and make sure that our values are accurate to what's going on between the two equilibriums, because they do deal with slightly different things. Now, as an example, we found that the value of our Kp was 3.9 times 10 to the 4, and we're still at 35 degrees Celsius. So now we're just going to plug in the values that we have, some of which are given to us and the other ones we had to find. We found 308 Kelvin here, because 35 plus 273 equals 308 as far as our Kelvin. And then we plugged in our values here to solve and find that the actual equilibrium constant based on concentration is going to be 2.5 times 10 to the 7. Now, we'll do a couple more practice with this in class, so don't fear on it. We're almost to the end of this part, and I actually think I might have to break this into a second video, but heterogeneous equilibrium versus homogeneous equilibrium. Now, homogeneous equilibrium is basically that all of the molecules that are involved are in the same state. So as we're looking at the first example here, all of them are gases. The second example, all of them are aqueous, or in an aqueous state. That will be a homogeneous equilibrium. Whereas a heterogeneous is where we're dealing with things that are in different states. Now, remember when we talked about something being a solid, that the value is always going to be 1. And so this actually gives us a little bit of a way that we can work through some of these kind of quickly. But We have a liquid and our solids both taken care of, also mixed in with our gases in more than one phase. So this is a heterogeneous equilibrium. Now, I think I'm actually going to break here and we're going to go ahead and do a second video where we're going to finish up dealing with this heterogeneous equilibrium as well as how to actually start to solve equilibrium problems overall. We're going to go ahead and break here, and I will see you in class tomorrow. Make sure you go over your notes and we'll pick it up from there.